Right. Very interesting topic today. High performance computing in AI, syringe use cases. So, how my experience will be relevant here is the last 2 years or so, been doing a lot of work on generative AI, and one of the key partnerships that I drive is that of NVIDIA. Right. I'm sure all of you follow the news. Anything to do with generative AI, anything to do with high performance computing, it needs a lot of GPUs. And when it comes to GPUs, NVIDIA is the unparalleled market leader, right? So today's session I plan to run based on a lot of video case studies. That'll be very useful for you as you interact with students in terms of what are the cutting edge innovations happening across the world via NVIDIA and other leading hyperscalers such as your Microsoft, Google, Amazon, and so on. So let's get started with today's session. I won't make it like too theoretical. Rather, I want to make it very application focused. There'll be a lot of videos. And at any point in time, if you have any questions, you can feel free to interrupt me and you can ask your questions. I hope my slide is visible to you guys.
Yes, sir.
Okay, thank you. So when it comes to high performance computing, one of the preliminary things is the what hardware stack that we use, right? So there's a switch naturally from a CPU to GPU architecture. Now, before I go into the deep top intricacies on what are the different use cases, I want to just make some certain clarifications on these basic terminologies, right? Because only if you get the hang of all this, you'll be able to follow the other stories that I'm going to talk about. Now, what's the difference between a CPU and GPU, right? Before I get into the theoretical part, I would like to start with a video that's a self-explanatory video that will help you get a very detailed understanding, right? So let me click on that. Okay.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Okay, so that's a clear difference between what a CPU and what a GPU is, right? So as you would have seen in the video, the first case it was a CPU architecture. CPU cannot do a lot of tasks in parallel. It can only focus on specific tasks, and that specific tasks it can do in certain amount of time, right? But in compare, when you take it to a GPU, it is much more higher. You have more cores. For example, if CPU is going to have only like 4 cores or 8 cores, GPU will have the likes of 100 cores or 200 cores, right? One core is one cylinder. And GPU is also more inclined to be very good at parallel processing. That is one of the reasons why NVIDIA has been very successful with its GPUs and how some of the generative AI applications has been very successful, right? So that's the predominant difference. I'm sure you have got it from that video. So the second thing is GPU based. It is not only having one paintball gun, but it is having multiple paintball guns. And the task that took previously like 15 seconds or 20 seconds, this can do in a matter of milliseconds, right? So just wanted to start with the depictions so that it will be easy for you guys to follow why the GPU is very important. So the other aspect is on the memory hierarchy, right? So memory hierarchy, this has been something that has been there right from the early 1900s, right? When people started working on basic computer applications based on Visual Basic, those kind of stuff, to where we are now, right? To the advanced stage that we are in now, it is still remaining the same, right? Be it CPU or be it GPU, it is still remaining the same. So when it comes to memory hierarchy, this is what I'm talking about, right? So you have your different layers, right? Be it CPU or GPU, you will have different layers like level 1, level 2, level 3, level 4. So level 1 may be the basic thing where you have the shared memory and everything. And as you go down, you have the further dimensions such as your global memory, your texture memory, and constant memory. How efficiently data flows from one level to another and how securely data flows from one level to another. These are some ways in which the sophistications are different when it comes to CPU and GPU, and obviously when it comes to GPU, which is much more sophisticated. That is the reason why we are having high performance and high efficiency. Efficiency in terms of cost savings, efficiency in terms of process savings, and efficiency in terms of time savings as well, right? Um, and then the interconnect technologies, right? So uh, again, in this case also I have a video to show. So what we mean by interconnect is when you have multiple GPUs, right? How can it work with each other? So you take a simple laptop or a simple computer, uh, different components are there within that computer or different within that uh, laptop. Now there may be multiple CPUs or there may be multiple chips. How does one chip communicate with other, right? So it might be using uh, this simple buses, what we call peripheral buses. That's the whole thing. That is also prevalently being used in most of the computers and laptops these days. But that is okay. That can be supported only to a certain data volume, right? Once you go to a volume above, when you want to work on high performance computing and when you want to work on generative AI use cases, then you will need a advanced thing. So that's where I think NVIDIA has released something called NV-Link technology, where one GPU to another can be, or one big device to another can be simply interfaced, and the data speed and the speed at which the data transfer happens from one interface to another can happen very seamlessly in a matter of seconds, right? So again, another quick video to show about it. We all live in the era of videos. Let me just show this to you. Yeah. So as you can see there, the benefits of NV-Link is very clear, right? So you have, so previously it was just like 12 MB like that, but now it has become much more easier. And in terms of the bandwidth also it can handle, you have obviously a 20-30x improve in performance, right? So that's another advantage of the NVIDIA NV-Link technology. And then what does you have a lot of companies like Nvidia, Intel, and the likes, right? But in spite, and you have AMD as well. So now AMD is second, first is Nvidia. So though these much companies are there, what makes Nvidia stand out? right? So especially when it comes to the evolution of high performance computing systems, three reasons are primary for this. One is the CUDA architecture. Now, previously when folks were learning CUDA, people were mocking them that it is like COBOL language. Why are they learning that kind of thing, right? But now, folks who know CUDA, they're all employed in NVIDIA. They're all getting like very good packages. So it is something that NVIDIA has made proprietary now, and CUDA language is kind of the backbone of all the HPC applications and all the GenAI suite that it is building on, right? All the AI apps it is building on. Now, what makes CUDA so special is what makes NVIDIA stand out is a parallel processing. What makes GPU stand out is a parallel processing. And for that parallel processing to happen, not all language can enable it. One of the languages, very few languages that can enable it very efficiently is the CUDA language, right? So it is NVIDIA proprietary framework, and it kind of helps in enabling the parallel processing, because of which all these GenAI apps has been used it, and people are getting very good efficiencies in terms of time savings, cost savings, and also process efficiencies, right? And the other thing that is enabling this is the tensor cores, right? So like I said previously, if CPU uh, is made of 4 cores or 8 cores, tensor GPUs are made of hundreds, 200s, like that, right? So in NVIDIA, within tensor cores, you have multiple configurations. So you have the NVIDIA RT GPUs. In RT, they will name it as 100, RT 100, RT 200, RT 50, and so on. That denotes the number of cores. The more the number of cores, the higher will be the configuration of the GPU. And then the higher the GPU, the cost will also be more, but the benefits that you will get, right? The data volume that you will be able to handle from a high performance computing perspective, that will also be very high. So it depends on use case to use case, depending on the use case that you are working, right? Like for example, if it's going to be a simple machine learning use case, then something like a RT50 itself should be sufficient. But if it's going to be a deep learning use case where there's going to be a lot of image and everything involved, then you go for a RT100 or RT150. But again, if you're going to use for if you're going to go for audios, if you're going to go for videos, then in such cases you will need to have the highest configuration possible, in which case you will go for a RT200 configuration, right? So in GPUs alone, I think the latest architecture what they released is called the Blackwell architecture. That is the very robust, and even in that you have a lot of configurations, and even their L series, A series, H series is also very famous. So beyond Blackwell, H200 is also something that is very popular, release from NVIDIA, right? So all these things are based on this architecture and technology only. And we already saw about what NVLink can do, right? So looking at tensor cores, so just wanted to quickly show you this, right? So this is one of the things why NVIDIA has been very successful, and why it is very successful is it. So there are two things when it comes to GPUs, right? When it comes to high performance computing, which is very important. One is your training, and another is your inferencing, right? What is training? Training is what you do before you implement the model, right? So you kind of train the model. So it's like you take a learner's license, and before you can get to drive an actual car, you just keep on training, right? So you don't drive it in main roads. So you kind of drive it in small streets, or you drive it in the early morning so that the traffic is less, right? And inferencing is what happens once the training is done, right? Once you deploy it in production, or once you deploy it in real time, what happens, right? So that's what is inferencing, right? So again, that's what you do after you get a driving license. You kind of take it out in an actual road where there's proper traffic and everything. That's what is inferencing, right? So for when it comes to the tensor cores, it is very optimized not only for training but also inferencing. So that is one of the advantages of this. And this is what I told, right? So NVIDIA Blackwell is the latest tensor core, latest architecture that has been released, and you have generation to generation. So this is something that we are seeing right from our childhood, right from the 70s, 80s. So Intel, when you take the likes of Intel, when we are using a lot of personal computers, you had the first generation, second generation, third generation, and so on. So like that, in iPhones, you have like 15, 16, 17, and so on, right? So it is very similar. So now we have the fifth generation. So there are some reasons why it is like very famous, right? So one is what kind of a precision it is able to give us, right? And then what are the cores that it is supporting, and how effectively it does both the training as well as inferencing. These are some of the reasons why these tensor core architecture kind of stand out, right? So these are just the fundamentals. So the CPU to GPU thing, how GPU is enabling these, how GPU is enabling this parallel processing. And then you have the memory hierarchy, which still remains layer by layer, so that the data mapping, everything is very optimal. Then you have the interconnect, where from a PCI bus perspective, you have kind of evolved onto the NV link from NVIDIA, which helps in high speed data transfer, which helps in handling high data volume. And then you also have the Tensor Core and CUDA architecture, which is responsible for the highly optimal performance of NVIDIA. So just wanted to set these fundamentals out to you before we go to the further case studies, right? And this is a CUDA architecture. This is a very proprietary language of NVIDIA. So the reason for the differentiation of this is you have four different frameworks, right? So first one is you have the parallel computing engines inside the GPUs, which makes the instructions sync with the core, and then high speed transactions happen. And then via the OS kernel, also this is also like a layered architecture, right? So this is also kind of like a memory hierarchy from a CUDA perspective. And then you have the OS kernel, where in that case also you have support for CUDA. And then in third cases, you have a set of drivers, again, that is CUDA supported. And then you have other things like device level APIs and language integration. So it not only works on CUDA, but it also has very seamless interface with the likes of legacy languages like Fortran and Fortran, but also the latest ones like there is a power cut at my place. I hope I'm audible, guys.
Yes, there was a small disturbance, but now it's back.
Yeah, there was a power cut, so I just joined from another line.
Okay. Okay, sir. Continue.
Mr. Murli, you had a question?
Are you changing the slide, because still the first slide only is there?
Yeah. Just give me a minute. Okay, so I was talking about the CUDA architecture. Is that visible to you now, Mr. Murli?
Yeah, this now it's changing. Earlier it was in first slide only.
Okay, sure.
Thank you, sir.
All right. Yeah. Yeah. So sorry for the interruption. So coming back, so we were talking about the CUDA architecture, right? So coming back to the memory hierarchy. So again, there are different layers because of which this CUDA is like very successful, right? So you initially you start with the set of parallel compute engines that is there within the GPUs itself. Then you have the OS kernel support, and then you have the CUDA drivers, and finally you have support for legacy languages like Fortran, but also latest languages like C, C++, and so on. And then you also have, depending on the application that you're going to build, right? Be it deep learning, machine learning, or even computer vision for that matter, you have different drivers available because of which NVIDIA has been very optimal, right? So that was the one of the things. And then when it comes to the key performance metrics, right? So when you build when you have a high performance computing system, right? And when you're going to build a lot of applications on top of it, what are the ways in which you can gauge the success? So these are some of the key performance metrics on which you kind of deduce whether the initiative has been successful, whether the investment is making sense, uh, whether you're going to get any return on investment, and so on, right? So the different parameters are, one is your floating point operations, which is called flops. When it comes to GPUs, like how you have megabyte, like how you have gigabyte, uh, these flops are computed in different speeds, right? There are teraflops, there are megaflops, there are million flops. So mostly when it comes to GPU, when it comes to high performance computing, the rating and scaling, everything is done in teraflops only. So that is one way in which you gauge, in which the speed of operations, speed of data transfer, everything happens. The other one is the memory bandwidth, right? This is again another huge differentiator for GPU over CPU. So in terms of uh, what is the data tranche that can be supported, right? What is the bandwidth? So usually it is all high volume only. It, minimum, I think you kind of do it in scales of gigabytes, right? Anything less than that might be good for a pilot, but when once you go for a full scale project, you work on minimum gigabyte level. That's when an investment for a high performance computing or an investment for uh, generative AI is going to make sense for you, right? The third one is on interconnect speed. That's what we saw in terms of the NVLink technology over PC buses, how NVLink is useful, how it is able to support more speed, and how it is able to kind of support higher data volumes, right? And the last one is in terms of power efficiency. This is where what is the amount of energy that you're going to spend on training? What is the amount of energy that you're going to spend on uh, inferencing, right? And as you deploy it in real-time applications, as you deploy in production and real-life applications, how we are able to scale out for the larger volumes. Initially, you start small. So the general approach that we take when it comes to high-performance computing is we call the framework as crawl, walk, run, right? So when I say crawl, we start at small level, we kind of show some success, we kind of show some incremental return on innovation. That's when the folks who are in charge of the budget also, they also get convinced. And then once we, like for example, let's say I'm working for a telecom company, right? This telecom company might be having like 100 products. Now these Gen AI apps that I'm building using high performance computing setup, I don't, they might not give authority for me to install for all their 100 products. So as part of crawl, I'll do it for 10 projects, 10 of their products, and then depending on the results that I get, then they, as part of the walk approach, they might uh, release it for another 20 more products. And finally, as part of run approach, you kind of do it for their entire set of projects, right? So that's a typical approach we take. It's called crawl, walk, and run, right? So these are some of the key performance metrics on which it is evaluated. So one is your flops, ideally in the tera range, and then you have your memory bandwidth, and then you have your interconnect speed. Since multiple applications will be involved, how the speed in which the data transfer happens from one application to another. And when you run a series of batch jobs, where do you start and where do you end. So all those becomes very important, right? So when I was working with TCS, I used to work for a large financial services provider based out of US, right? Daily when stock market runs, uh, before the stock market runs, we'll run a series of 100 jobs to mediate the prices, and then after the stock market closes, we'll have to update the prices again. We'll run a series of jobs again. All these jobs will be interdependent on each other, right? So if one job is going to fail, then it affects a series of other jobs, and then you'll have to start the job from beginning, right? So this is where the speed in which the job completes, how cohesively one job starts after another, and even if one job is failing due to an error, how soon you can bring up the job, and how soon you can ensure that the whole series of jobs run and the stock prices are getting updated becomes of paramount importance. Yes, that's one of the reasons why uh, the highest adoption for generative AI is seen from financial services, right? So you'll be able to, in a very quick manner, you can run the jobs, and even when some errors or anything happen, you'll be able to bring back the systems quickly. So again, that's where interconnect speed becomes very important. So that's the reason why financial services and healthcare, they are seeing the largest application in terms of high performance computing and generative AI. So now let's look at what are some of the top players doing, right? So when you take the like of Nvidia, when you take the like of Microsoft, Amazon, Azure, Azure is Microsoft. When you take the like of Google, what are they doing? What are the offerings that they have? And I have just kept one case study from each of those guys, so that will be very interesting for you, right? So when it comes to NVIDIA, we have already seen briefly about what NVIDIA has. They have a lot of GPUs that is specifically uh, focused towards accelerated computing, right? And then they also have something called NVIDIA AI Enterprise Platform. So a lot of people think NVIDIA is only about GPUs, right? It is not only about GPUs. So they also sell software. That's what is called NVAE. It's called NVIDIA AI Enterprise. So the cost of it comes to $2,000 per year. And for some of the high configuration GPUs, they also give it for free. But if you're going to start with basic configuration GPUs, they kind of make you pay for the license as well. So in my current role, we have done a lot of projects using NVAE, and one of the reasons why this NVAE stands out is, though you have the likes of Microsoft, Google, and Meta using a lot of NVIDIA GPUs, they won't be having access to the property details of GPUs, right? Like at what core level, such kind of schematics they may not have access, but that is access that NVIDIA has, since it is their IP. So what they do using all such information, they have kind of optimized their NVIDIA AI Enterprise suite, because of which a job, let's say the bank example that I gave you, right, where one job has to run after a series of other jobs, using a Google platform or a Microsoft platform or a Amazon platform, if you can run it for, let's say, 100 minutes, if you do the same using NVAE, you can maybe run it for 80 minutes, right? Because their software is suited to have that optimal performance, and provided you do the right fine tuning and everything, you will be able to even make it run at 60 minutes and 70 minutes as well. So that's one of their biggest advantage. Now, if you look at the DGX superpod architecture, um, this is what it looks like. Guys, I hope this schematic is visible to you. Can one of you confirm whether the image is visible, guys?
Yes, sir. Yes, yes.
Okay. So as you can see, this is a super pod architecture, right? So this is, so when you take high performance computing, so this is what the configuration will look like. So as you can see in each, I think you have close to 8 rows in this, in the top, and 8 rows in the bottom. So in each, so in total you have like 16 DGX H200 GPUs. So together that 16 DGX GP100 GPUs, they'll be able to support close to trillions and trillions of data. And this might be ideally for a financial services or a healthcare application. mostly in the deep learning space where you need to have a lot of you need to have support for a lot of video data, and you need to have a lot of support for audio data, right? So this is one of the DGX superpowered architecture. And coming back to the deck, let's look at a couple of case studies, right? So the first one is on NVIDIA Cambridge supercomputer. So I think King's College London has used this facility, and they have kind of developed a solution. We look at that, and there's also another live solution where real life translation is happening, right? So let's look at both of these, and then I'll probably explain to you in detail, right? So let's first look at this. I will select the other one as well so that it becomes easier. Yeah, so let me go back here.
UK healthcare faces enormous challenges, which we believe can be in part solved using artificial intelligence and new technology. UK healthcare has access to far more data than was ever previously available. And this enormous amount of data can be used to help scientists predict disease, treat disease, and give precision treatment to patients. NVIDIA's mission and purpose in healthcare is to enable scientists, researchers, doctors to solve the challenges of modern healthcare and medicine by using artificial intelligence and accelerated technology. King's College London is a world leader in medical research, so they were a very natural partner for me. We really wanted to work with UCL to accelerate their research using NVIDIA technology. At King's College London, we are working jointly with our partner hospitals and university collaborators to create platforms that can collect data and do the kind of analysis, research, and training of algorithms at the scale that is necessary to solve real-world problems. One of the main issues that we had so far was the lack of availability of hardware, and this is exactly where NVIDIA can come in. A lot of the study that currently happens in the healthcare setting is built around patient data. And obviously, as you can imagine, patient data has a huge amount of privacy issues. If we can generate synthetic unstructured data, we can do as many studies as we want without having to jeopardize that patient's privacy. So ability to generate synthetic data not only gives us the ability to understand how different factors affect the brain or your anatomy or your pathology, but also allows us to do this research having very minimal impacts in privacy and governance. We are creating algorithms that can learn the patterns and what imaging data looks like, more specifically what brain images look like, and algorithms that can imagine new data sets where we can control the characteristics, for example, the age of the patient or the pathology that the patient suffers from. We can now ask our model to generate an almost infinite amount of data. We can start tackling problems such as understanding how diseases affect the brain, understanding when abnormalities might or might not exist, but also being able in the future, for example, to develop new drugs and new treatments and simulate what these effects might look like in silico, inside of a computer chip, rather than trying it on people. If we can generate brains and we can distinguish brains that are normal and abnormal, and for example, if we know what a healthy human brain looks like, we can also identify when an image that we're observing deviates from that pattern of normality that we expect. You can then tell the clinicians the location where that abnormality exists and why is that kind of normal, which means you can help identify pathologies and diagnose patients. We really use the full NVIDIA stack. The latest A100 80 gigabyte GPUs, the DGX A100 server, PyTorch, we used cuDNN in order to visualize these results. We've experimented with using Omniverse as well. We've got some really encouraging results from Omniverse from this task, and we really think that Omniverse can be used by physicians and researchers in the future for enabling them to understand how to interpret their research. Cambridge One provides 400 AI petaflops of performance, so we can allow scientists and researchers in healthcare in the UK to perform tasks which they were previously never able to do. We're going to be able to perform AI training, process huge amounts of data to a scale never before possible. We also want Cambridge One to be a hub for healthcare research community. We want people to get together, innovate, and develop new healthcare technology to an unprecedented scale. We are also providing a tool, a software to extend series of models to the community so that you can generate your own brain imaging data, but you can also apply the software to your own medical images of other body parts and other diseases. So you can generate data of something that isn't visible to you. We would like to see scientists and researchers push the boundaries of their endeavors, push the boundaries of science, understand medicine, understand healthcare to levels which we've previously been unable to do.
So, I'll share all these links in the deck that I will share. All these links are there, so you can also go through it later. So, as you would have seen in this video, you would have got a view into the massive infrastructure that this King's College has. And if you look at the speed, they were talking not only tera, but they were talking about petaflops, right? And they are also talking about a huge volume. And you can also look at the kind of impact that they are making, right? So they no longer have to use the actual patient medical information about brain related data and everything. They can create it artificially using the synthetic data generation solution, and using that they'll be able to do a lot of permutations and combinations, and they'll be able to do a lot of advances in the field of medical treatment and the healthcare treatment, right? So this is one of the use cases that using this NVIDIA supercomputer, King's College London is working. That's one of the things that I wanted to show to you. And the other thing is something called blueprints, right? So what is blueprints is, this is like a package what NVIDIA has released, like how we have instant noodles, like how you have this instant tiffin items and everything, right? You have instant dosas and everything. These guys have released instant packages where you can kind of download the package, install, and you can develop applications. So if you look at the blueprints, again, you have one for RAG. Most of you might be knowing about RAG. So that is a basic architecture in which you're able to kind of send in a lot of data, and you're able to kind of get a lot of contextually relevant responses, right? And then they have something for the protein binder design, and they have something for the industrials from a digital twins perspective. They have something for automobile, and they also have something for AI assistant for customer service. So like that, they have multiple things. They also have something for vulnerability. So this is basically like a ready-made package which you can download, which you can install, and you can start using. Let me just take you through one of the things, right? So let's look at digital humans, right? So again, this customer service is one of the areas that is hugely hit by generative AI. A lot of things are getting automated. So here you have like multiple things, right? So you have two different characters. This is not actually a human. This is a character or a graphics that is being rendered by generative AI. So here in the demo, what we'll see is I'm going to give some inputs in audio. In real time, that audio is going to get converted to text. And
Sorry
by
to interrupt
understanding,
you, sir.
yeah.
Sir, your PPT is not visible. You didn't share the PPT.
No, I'm not talking about the PPT. I'm sharing a page. Is that not visible to you?
No, it is not visible.
Just give me a minute. Okay, is it visible now, please?
Yeah, it's visible.
Okay. So this was one of the blueprint what I was telling, right? So you have multiple blueprints. I selected the one for digital human configuration. So here basically what happens is the image that you see here is not actually that of a human, but it is something rendered by graphics. So it is using a package called ACE. It's called NVIDIA ACE, which is for their custom digital avatar. So there are two different avatars here. So one is James. James is a digital avatar that is trying to talk on NVIDIA products, right? And then you have another character called Area, which is trying to talk on customer support, general customer support. So in both these cases, in my demo, what I'm going to show you is how in a real time the audio input that I'm giving is going to get converted to text, and how the text is going to be hit against a standard knowledge source, and how you are getting a response in a matter of seconds in real time, right? So this is one thing that is getting huge traction in the customer service space, and that's the reason why I thought I'll show this to you. Let's start with James. So I'm going to click on James. Hi, James.
Hello, how can I help you today?
I would like to know about NVIDIA's H200 GPU.
NVIDIA's H100 GPU is a powerful AI accelerator featuring 4th generation tensor cores, a new transformer engine, and NVLink technology for high performance AI inference and training.
Guys, were you able to follow that? Can one of you respond? Were you able to hear his response?
Yes, sir, but little bit disturbances are there.
Okay. Okay, so I've placed this link in the deck. You can also try this out. This is free only. There's no subscription or anything. This is free only. So
Okay, sir.
this is one example. So if you look at how it works, so this is the architecture, right? So basically, once I pass the input, the audio to speech text conversion is happening, and across a lot of NVIDIA libraries, a lot of processing happens, and finally the text after getting converted sit against a knowledge base, and then you are getting your output. All these expressions are happening in a matter of seconds. That's the advantage of going for a high performance computing, right? Now let me show you probably one more example. Let's talk to area.
Today.
Hi area, how are you?
I'm doing great. Thanks for asking.
I lost my debit card. Can you help me?
I'd be happy to help you with that.
So I actually lost my debit card on the way when I was going to office in metro train. So what is the procedure that I should follow?
I'm so sorry to hear that. You should immediately contact your bank's customer service to report the lost card and request a replacement or temporary card.
Okay, guys. So I hope you are able to follow that. So again, this case is a customer support person. So I'm telling I lost my debit card. So she's been very empathetic. She says, "I'm sorry that you lost the card," and she guides me, asking me to contact to the this bank's customer support person. So this is a basic thing. So that's why it is able to answer only primary questions. But once you do fine tuning, once you have a proper package and everything, then as per the branding guidelines, it can even do that blocking for me as well, right? So these days we are seeing a lot of evolution in terms of agentic AI and everything. So if you do a proper version, it should be able to actually do that cancellation for me as well. So just wanted to quickly show you these use cases, predominantly from an NVIDIA perspective, so that you will get a first-hand visibility into what are some of the real-world applications that NVIDIA is working on, right? So this is on the NVIDIA stack. So coming back to the deck, so let me share it again. So, okay. Okay. Yeah, we see about this. Yeah. So the next one is on Microsoft Azure, right? So Microsoft also, all the GPUs that they have is predominantly based on the NVIDIA GPUs, but they have their own set of solutions. They call it the Azure high performance solutions, right? So using that, they have like a lot of use cases. They have also launched a series of virtual machines, and they call it the NDV4 series. And they also have something called InfiniBand networking, which is again a set of Ethereum-based protocols and kind of various models that they've released. That is predominantly focused towards high performance computing, and that is optimized or kind of fine-tuned to get the best of performance from the NVIDIA GPUs or Intel GPUs for that matter, right? Now, if you look at this, this is one example of what Microsoft has done for Wave, right? So using their high performance computing suite, which is being powered by NVIDIA GPUs. So I'm going to click the subtitle on so that you'll be able to follow this. Yeah. So as you saw in that video, so it is again self-driving, right? So you have like a Tesla, you have like a Waymo and everything. Plus, when it comes to self-driving cars, again there is a huge amount of data involved, right? So you have sensors on top, you have cameras, you have proximity sensors, you have multiple sensors, you have multiple cameras, and the cameras are 360-degree, right? So it should look at the left side, right side, forward, backward. There's obviously going to be a huge amount of data involved, and we're not talking about simple static images, right? So videos have to be there, and from videos frames have to be analyzed, and only when a proper understanding there, then it will be able to kind of take the right decision, right? If for example red signal is there, I should stop, right? And then a dog is in front of me, I should stop. So all these happens only via training. So this is where I think it was a good implementation that Microsoft had, this company called Wayme, during their using their high performance computing setup, right? Another thing is about the OpenAI's GPT training infrastructure, right? So again, if you take GPT, I think the GPT-1, it had like 178 billion parameters, but now the GPT latest 4, it has close to, it has gone over billion, right? It has like close to trillion parameters, and all of you would have followed what happened with DeepSeek as well, right? So they were able to give a much more better performance at one tenth of the cost, right? So As we progress, we can expect more such revolutionary changes coming from these AI companies, and ultimately, as the end users, as the business users, we are all going to get some benefit out of this, right? So this is about how SC Lauder. So SC Lauder is I think they are in the beauty segment, right? So what they did was using Chat GPT. So SC Lauder is in the beauty segment. So they have like hundreds and hundreds of products, right? So and for all those products, like there were a lot of questions from people in terms of what whether it is tested on any animal or whether it is tested on any synthetic items. So all those things leads to multiple permutation combinations. So these customer support agents are getting a lot of questions like this, and they were not able to answer. So that's when they used this Chat GPT, and using that they were able to build a very robust data source. And using that data source, all these questions were queried by the support agents, and they were able to answer it in a matter of seconds, right? So this was one of the huge thing that SC Lauder did using Chat GPT. Okay, so you can look at this video later. In the interest of time, let's kind of look at the other players and some of the other interesting use cases as well. But here, basically, the whole idea is they had a huge amount of data using this high performance setup. They set up this knowledge source beautifully, and using the knowledge source on top of Chat GPT, they were able to uh, completely cut down on the knowledge consumption time, knowledge retrieval time, and they were able to kind of reduce the turnaround time for questions being answered to their customers. And at the end of the day, their staff, the customer support staff, they are also happy, and the customer are also happy because whatever questions they have, be it very complex or be it very simple, is getting answered in a matter of seconds, right? That's what SC Lauder had did with using OpenAI software. And then you have Amazon Web Services, right? Again, another huge player. Now they launched something called parallel cluster. That is again optimally trained at the parallel computing, right? How quickly you can complete process in parallel, so that you get a lot of savings in terms of cost, in terms of process efficiency, and also in terms of time processed, right? And they also launched some specific instances based on EC2 P4D that will very well work in sync with NVIDIA GPUs, and that will promote parallel computing. And they also launched their own chips recently as a competition to NVIDIA. It's called AWS Titanium, and it's called AWS Inferentia, right? Now, if you look at AWS Titanium, so as you can see, some of you might have seen that Annapurna Labs, right? It's actually a Indian company only. I think it was acquired by AWS, and this is one of the things chips that they've released that is very optimal towards training, right? It's called AWS Trainium, and the other thing is called Inferentia. Again, as the name suggests, this chip is optimally towards high-speed inferencing, right? So again, in the interest of time, you can look at this video later. So this is again another chip that was launched by AWS, which will kind of promote high-speed inferencing, right? And Perplexity, I'm sure all of you have heard about it. Again, built by an Indian. It's a huge moment of pride for us. So they had actually in large scale used AWS using the AWS HPC computing. So that is something where the user base is growing daily, and the kind of work that they do, right? They kind of evolve. They've gone one step above Google search, right? So I'm sure some of you here would have used Perplexity. Anyone here who has used Perplexity on day-to-day work can just show your thumbs up emoticon. Have you guys used Perplexity? Any of you who use Perplexity, guys? You just give me a thumbs up. Just send a message or something. Okay, not a problem. Okay, so coming back, guys, I hope the deck and videos are visible for you. Are you able to follow this?
Yes, sir.
Okay. Yeah, so let's look at how the CEO is talking, right? So in terms of how they were able to use this AWS setup and how they were able to scale their product, which is like a competition to ChatGPT, Copilot, and so on, right? So in this case, he's talking about AWS Bedrock, right? So that was a proprietary solution of AWS. So how he was able to use that and how he is able to kind of ensure Perplexity as an app, concurrency is not getting affected. A lot of users should be able to use it in parallel, should be a scalable solution, and then performance wise, latency wise also, right? So the user should get a response as soon as he gives a prompt. He shouldn't be kept waiting for long. So all these are some of the aspects that he had covered, right? That's a good introduction. And the next one is on Google Cloud, right? So Google Cloud also, they have their own high performance computer toolkit, and they don't not only rely on the GPU, they also have something called tensor processing unit, which is one evolution above CPU, but one it is one level below GPU in terms of performance, speed, and everything, right? So I think this, yeah, this is how a TPU pod looks. Almost similar to the GPU architecture that we saw, but there will be some subtle differences. But it is much more advanced than a CPU, right? And they also launched their own instances. It's called A2VM and DeepMind, right? So DeepMind has been their proprietary thing for quite a long time now. So DeepMind is a company that kind of developed models that defeated grandmasters in chess, that kind of repeated grandmasters in a lot of games, right? like DeepGo. So their company, they have something called, that was acquired by Google. They have developed something called AlphaFold infrastructure. So using AlphaFold infrastructure, uh, their people are working leveraging this high performance computing to kind of solve a lot of very complex medical problems, kind of solve a lot of very innovative need of the heart problems, right? Like for example, plastic consumption, right? So at this rate, if you keep on going, then the world will be filled by plastic. Then we'll be led to even more chaos, right? So they are using deep mind to see whether they can develop a bacteria that can eat these plastics, right? So that is one lot of interesting projects like that they are working. Maybe we'll just look at one of those. Yeah, so this is one where they're kind of trying to solve the solution or pollution problem. So as you can see, in this case, they are using Google DeepMind. They are trying to develop advanced algorithms that can help in creation of this bacteria that can consume the plastic, right? So this is one interesting use case. And the other one is, I think they're doing for the global food supplies, right? So a lot of things, 40% of the crops are lost due to diseases, right? So how they can develop like these disease resistant bacteria that can ensure you don't have to use a lot of pesticides and everything, right? So that's another interesting use case that they are working on. Instead of these pesticides, how they can kind of develop disease resistant varieties that pests won't be able to. So this is another interesting application that they are using via this Google Deep setup. So those are some good examples that I wanted to talk about in terms of what are some of the leading hyperscalers are doing, right? And what are some of the other important concepts that we need to keep in mind when it comes to high performance computing, right? So, like I said, training is a standout feature for them. Distributed training is a very important concept for them. And within distributed training, you have a lot of concepts like data parallelism, model parallelism, pipeline parallelism, and communication patterns, right? So data parallelism is nothing but when you have a single data set, the data is getting split and the data is being assigned to multiple shards, and within that shard there will be, that's what you guys in the CSC terms, you will have like sharding, you'll have CRUD operations and everything, right? So this is the same. So where there will be multiple shards, the data will be processed across multiple shards and you will have a version ready. So what is going to happen is the data is not getting replicated, but the model is only getting replicated, and finally the results will be combined together to get a very optimal output. So that is data parallelism. Then model parallelism is where the data is not getting split, but the model is going to get split across multiple instances. And again, depending on use cases that you have. So let's say you have use cases where there's a lot of images, such kind of things, then you go for data parallelism. But when you have a lot of rocket science data, when you have a lot of mathematical data, there is a lot of equations and everything, then you go for model parallelism, right? Uh, and pipeline parallelism is again very similar to data parallelism, but the only difference is you will have both the forward propagation as well as the backward propagation. And once the backward propagation is done and all the errors are going to get solved, then the output kind of fixes itself. And this is especially useful when you are going to have a lot of reward based models, right? Like for example, when you are going to deduce whether a person is going to default or not, or when you are going to kind of try to identify the customer lifetime value. In such cases, this will be of huge use to you, right? And within memory optimization, you have multiple techniques. You have gradient checkpointing, you have mixed precision training, and then you have memory efficient attention mechanisms. Again, these are various techniques within memory optimization that will help you cut down the processing time that will help you bring in a lot of savings, that will help you bring a lot of process efficiency. So which strategy that you want to use, it depends on what kind of use case that you're working on, right? Like, for example, if it's going to be simple text data, then simple model charting will do. But if you're going to have a combination of rich data, like a combination of images, video, audio, then you go for mixed precision training. And if you're going to have a series of bad jobs, so those kind of things, then you can go for gradient checkpointing. So what kind of techniques you apply depend on what kind of data you're going to use, whether it's going to be structured data, whether it's going to be unstructured data, and whether it's going to be any rich data involved. It will only those will determine what memory optimization technique you're going to use, right? And then you also have a set of software frameworks, like most of them are open source. So you have the likes of Haro Word, you have the likes of Deep Speed, and then you have the likes of Megatron language model, and you also have the NVIDIA NCCL framework as well. So these are also something software frameworks, mostly open source, that are given by these hyperscalers like NVIDIA, Google, Microsoft, etc. That will help you get towards the workload optimization, right? Uh, and from a real world application perspective, there is a lot of talk going on large language models, right? When it comes to large language models, some of the requirements are you need to be very careful on what infrastructure you require to train the model, and then what is the infrastructure that you require to kind of optimize the inferencing, right? So inferencing is the speed at which you're going to get response based on the training that you've done, and what cost you have. So that is also something that will play a very important role, right? So let me show two quick examples here. So one is, this is based on what NVIDIA did for a company called this is for a company called MDocs. So what they did was, again, it is a use case in the customer's support space. So
ஆஃப் பண்ணிட்டேன், அதனால கரெக்டா ஆரம்பிக்கணும்னா சொல்லுங்க.
sorry, what was
அதாவது
that?
நீ தானே கொஸ்டின் ஆன்சர் செஷன் ஹேண்டில் பண்ற, சரி இப்ப நான் அதை பண்றேன், நீ இதை பண்ணு சொல்லணும்.
Some of you has to go on mute. Okay. So they did this something for MDocs. This is again in the customer support space. So here again, what they did was they had a huge amount of data, and they didn't want their customer support staff to answer the same questions again and again, right? So those kind of things, using agents, they were able to modify, and because of this, they were able to get, the employees were much happy, and the questions were also able to be answered in a very quick manner. So the customers were also very happy at the end of the day. Let's look at what they did. So as you can see in this case, there was a query that says, what's on my bill? How am I using stuff? And did anything switch up since the last bill? So it is instantly giving a response, and looking at the knowledge repository, it is also able to tell based on the data in which it is trained. So this is the actual inferencing, right? Based on this prompt, how it is able to respond. That's what we call inferencing. That is one of the predominant things. Why is it possible? Is because of the high performance computing setup, right? So in this case, if you see, the prompt is there, and based on the prompt, you are able to get an instantaneous response. So you're getting a detailed response based on what bill he has got. So he's got a detailed thing also, like what is the unlimited thing and what is the split up, and whether he wants to buy something. So it is prompting him towards action as well. So all this transaction got done in a matter of 30 seconds, right? That is another huge advantage of a HPC setup. So that was one of the NVIDIA example from a telecom industry. And the other one, this is the Jetson Orin computer, right? So this is Jensen, the CEO of NVIDIA. Most of you might know him. So 2 months before, NVIDIA launched something called Jetson, right? So it's just in the size of a thumb. In the size of a thumb, they've kind of launched a generative AI powered supercomputer. And charge wise also is like close to $2,000 only. So in this video, he'll be showing about the Jensen O-ring. Let's quickly look at that. Just the size of a palm, right? That has the capability of a supercomputer. So in a thumb size, you're able to, using this thumb size setup, you'll be able to kind of develop very advanced applications, right? So this is the NVIDIA Jetson Ori supercomputer. The next one is on the computer vision, right? So when it comes to computer vision, the top applications being medical imaging and then autonomous vehicles, and then you have satellite image processing. Um, Again, here also, NVIDIA, Microsoft, they're all doing huge amount of work. So computer vision is basically a lot of image, a lot of videos going to get captured, and what is the analytics that you and insights that you can build on top of that, right? So that's what computer vision is about. Let's look at one of the examples. So this is again using NVIDIA ACE framework. So this is a digital human, right? So we looked at an example. This is a digital human example that we saw. So this was the person whom we were talking to, right? I hope you are able to recognize this person. So I think you get the hang of it, right? So basically, that's the ACE package from NVIDIA, using which a lot of computer vision stuff get done, right? So like digital avatars, not only from a customer support perspective, but from a healthcare perspective, from an education perspective also, there is a lot of interesting applications, right? So That's another interesting use case from a computer vision perspective. And the last one is on scientific computing, right? So again, this is again where the high performance computing is going to get a lot of application. How do you use it for weather prediction? How do you use it for advanced scientific calculations in terms of molecular dynamics, also quantum chemistry and so on, right? So this is again one example from AWS, Amazon, where they're doing a lot of work um, for the US missions. So this is specifically this AWS model, and that is being used in NASA Houston. That's the example we'll be looking at. So here, as you can see, using these models, advanced models, they are able to kind of process images from Mars rover. They're able to use that for doing a lot of scientific calculations, and they're able to use that in their advanced scientific and space missions as well. So this is a specific domain within AWS. Is called aerospace and satellite, using which they are able to do this, right? And from a future trends perspective, again, we are all eagerly awaiting what is going to happen from a quantum computing perspective, right? So 1 month before, there were a lot of interesting updates from Google, but 2 days before, there was a interesting update from Microsoft. I'm not sure how much of you saw this, but let's look at this quick video, right? So they've released something called Majorana 1, which they are telling is very powerful. It is capable of holding a lot of qubits, using which they are telling, compared to the existing applications, they will be able to make it 15 times or 20 times more powerful, right? So that's what they had launched. Let's quickly look at this. Yeah, I think you would have got some basic idea. Maybe when I share this deck, you can go through this video in detail. So basically, they've got a very advanced thing in quantum computing using this Majorana particle, using which they are saying a lot of immense possibilities are possible. Photonic computing is another interesting area within quantum computing, using which they'll be able to store and process information in a much more optimal manner. The third one is on energy efficiency challenges. So as of now, for this training to happen, for this inferencing to happen, a lot of water is getting consumed, right? So already as a species, we are facing a lot of water shortages. So how do you make it more optimal? How do you reduce the energy that is getting consumed? That's also something that we are looking. And also when you want to scale it for large factors, how do you do it, right? So these are some of the interesting things based on which we can expect more updates, right? So I've placed all these links in this deck. You can feel free to go through that, and in case you have any questions, you can let me know.